Hello there, learners of mathematics and fellow math enthusiasts. In this video, I have classic word problems to solve that typically textbooks would guide the learners through some knowledge and use of algebra. However, in this video, I'm going to show you how to solve these word problems using patterning and a piece of a string. Very, very simply, I'll put some sense into this algebra gibberish that's presented in the textbooks. These three word problems here are actually one and the same problem. For starter, you can see that the number 1557 is featured in all three of them. And if we read it, which we will do, you can see that these at their core are the same things, just dressed up and sugar-coated differently. So the first one on paper seems to be about a rectangle. The second one is about three numbers. And the third one looks like it's about three types of goldfish. But it could be marbles in a bag instead of goldfish in a fish tank, or it could be library books in a library, whatever, same thing. You're getting the idea soon here. So let's go back to the rectangle here. What do we know about this rectangle? We know here that the short side is a quarter of the length. And this expression here is really important, a quarter of the length. The short side is. And the sum of two long sides plus one short side equals 1557. So only three sides are added here, not four. It's not perimeter, just only three of them. So two long sides on a rectangle and one short side. Now, what kind of rectangle is this? If we start with a square here, kind of something like this, just to visualize it, the square is a rectangle, a special one. It has two sets of parallel sides and four square corners. So rectangles can be a little longer, and that's a stubby or chubby rectangle, or they could be longer and skinnier. This is one of those skinny rectangles where the width of it is a quarter of the length. I'll show you in a different way in a sec. But let's take a look at the other two word problems. How are they all the same? So in the next one, with three numbers featuring, two of the numbers are the same. And it's easy to see that on a rectangle, two sides, the two long sides are the same. And the third number is a quarter of either the first or the second. So this one is essentially the same thing. And even though it's asking which are those numbers, that's exactly what the first one is also asking. How long are the sides? Same as the which are those numbers that are the sides on a rectangle. And the last one about goldfish, marbles, or books in a library, two colors, there are three colors there, and two of the colors, say red and green, are equal in number, just like on a rectangle. The two sides are equal in length. The two long sides and the short one is, or here the third one, the yellow fish, are different. They are a quarter in number, or either the red or the green fish. So you can see that these three math problems or word problems are exactly the same. They're just worded differently. So how do we solve these without algebra first? For that, let's have a step back here, and I want to point out that you need to recognize that these word problems, or this one word problem, is what's known as a fixed length problem. And of course I have a piece of a string here that has a fixed length. Fixed length problems abound anywhere where in manufacturing, for example, there's a fixed length to the particle board or plywood that's being manufactured, from which you can make countertops. Of course you can join countertops together mechanically, but that's different. So there's a fixed length to the countertops, or the PVC edge that runs around the countertops, there's a fixed length to it. if this PVC edge comes in pre-cut length, there is a maximum size of table that you can make with a fixed length edge that the edge can wrap. So let's use that countertop edge idea here to look at this piece of string, which I'm gonna hold like kids play with it, although they play with a loop, but I'm gonna be making 3 sides of the rectangle here, so I'm gonna do it slightly differently but somewhat alike. You've seen kids doing this, yes? Looped around the fingers, and they are passing the string in different configurations from hand to each other. Whatever the name of that game is, you've seen them play this way pretty much everywhere in the world. I know I haven't been everywhere, but close enough is close enough. And you can see rectangles made wider and not so long, and skinnier and longer rectangles with a fixed length string, because this is a fixed length problem. And in one of these configurations, this short side here in my left hand is going to be a quarter of the long side. The long side is easy to visualize for quartering it, because you can half the length easily and half it again. Half over half is a quarter, 1 quarter, 2 quarters, 3 quarters. Here is the 4 quarters for the length. And so at one point, the short side can be made a quarter of the length very easily. So this visualizing is really critical to solving this word problem and many word problems in math. And I would like to make a sketch of this visualizing, because there is a pattern to the madness here. So this isn't to scale, this is just a concept sketch here. So when this one is 1 unit long, and this one is also 1 unit long because they are equal in length, and this is a quarter. Oh, that's very ugly, but very ugly fraction, but this is a quarter of the long side. Now I don't want a fraction here for the short side, so I'm going to change it to 1 being here. And if the short side is 1 unit long, then the long side is going to be 4 times as long, because that's how the short side is a quarter of the length. So there's half and half the half, so there's the quarter to it. Now a quarter of 4 is 1 there, so you get it. And if of course this side is 4 and this side is also 4, because they are equal in length, the long sides are. And the pattern can be extended here and drawn to full scale actually. So here the sum of the sides are 4 plus 4 is 8 plus 1 is 9. So drawn to scale, the skinny rectangle looks like this. So it's a 4, 4, 1 rectangle. So that's the short side, this is the long side, and this is the sum here, which is 9. And the pattern can be extended. If the short side is made 2, the long side will be 4 times as long, because the short side is a quarter of the long side. So if this is 8 and this is 2, of course this one is also 8 there. So 8 plus 8 is 16, plus 2 is 18. So at 1, the short side being 1, the sum is 9. At 2, the sum is 18. If we keep continuing this pattern, eventually we're going to get to 1557, hopefully sometime today. And we don't know what width and we don't know what length corresponds to this rectangle. But the numbers can be plugged into an Excel spreadsheet, because these numbers make an easy T-table. Have a look at this spreadsheet on the screen, and it is looking like this. There's the short side, there's the long side, and the sum of 3 sides, and exactly the same figures here are featured. So I just put in 1 and 2 for the next one, and in this cell I'm just quadrupling, multiplying by 4 whatever is in this cell, and this makes the sum of 3 sides. There are 2 of these, so I'm doubling that cell content and adding up onto it, and I can just very simply copy the formula down and oops again, I'll get there. Copy the formula down and there, the 9 times table you can see here for the sums. And in Excel it's really easy to extend this not timetable, what is it, t-table down. We're at 600, getting to 1557. Yes, it takes a bit of time, but we're at 900. But of course, doing this manually, we're almost at 1557. Doing this manually would be a little bit unreasonable, but a t-table that people can make on a small scale can be extended. There, 1557. So this is the width, this is the length, and this is the sum of the 3 sides. So there, problem solved. So the rectangle, or the number of goldfish, or the sum of 3 numbers are 173, 692, and 692 again, to equal to 1557. So this is how it's solved with patterning and the t-table and a little bit of common sense or visualizing. Now, I want to point out that in the textbooks, this is how similar problems look like. Here you have a rectangle where the width is 2 units less than the length. Instead of being a quarter of the length, it's 2 units less than the length. And this is how it's worded. 2 inches, whatever, 2 less than the length. So that's the algebraic expression that's key to it. And the perimeter is whatever. This one has a perimeter instead of 3 sides. So it's the same problem essentially. And here is a B version of this with a rectangle, a skinnier rectangle looking like that. And this is worded as 4 units, 4 more than twice. Something is 4 more than twice in it. So that's the algebra part. And this is how the 4 more than twice the width looks like, or is written in algebra there. I can't highlight that, but it's there. Now, let's solve this original here using algebra. So how do we write a quarter of the length? A quarter of the length is written as a quarter, like with the fraction a quarter, and length is written as L. So what we have for the 3 sides of a rectangle is length plus length, those are the 2 long sides, and a quarter of the length, and they all add up to 1557. Practicing this skill here to create this line of equation here is really critical. How to peel it out of the text where all you see is usually words, even the number words are just typed up like so. It needs time and patience and practice. Okay, so if you can't write this equation, just needs patience. Okay, you can reverse engineer it from the answer key or something like that, but this step is really critical to go from blah 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 to equation. There, snapped out. So how do we solve this equation? We combine like terms, and length plus a quarter of the length is 2 1/4 length. 2 1/4 can be written as a fraction or a decimal. I just went with decimal. Why not? We can combine like terms because we have the length of a string plus the width of the rectangle plus the rest of the length here. It's easy to see that you can combine like terms into one continuous fixed length equaling 1557. So it is possible to combine these like terms. Algebra rules come from common sense and life. So after dividing both sides of the equation by 2.25, you get the length equaling that number. What is the short side then? Well, the short side is a quarter of this length, so we just divide this by 4 on a calculator and you will end up with the same 173, exactly the same as with patterning, not surprisingly. So the the patterning or the algebra, the patterning doesn't really need to be checked if it's calculated correctly, but the equations do need to be checked. So make sure that the three numbers do add up to be 1557 as requested in the specifications here. So this is how to work with word problems. Instead of algebra, you can work with patterning. Either which way, it needs imagination, it needs visualizing, and it needs practice. So be patient and give yourself a lot of leash on this and a lot of time. Learning algebra is not quite intuitive, and it's just not easy. Eventually you can do these in a heartbeat. A practice problem like this here in the book, it's solved step by step. If it takes you for an hour or whatever length of time for your first or second word problem, that's an excellent start. Eventually that 1 hour is gonna come down to, I don't know, within 2 minutes, something like that, when you're really proficient at seeing through a maze of words and solving these efficiently.